Hello everyone, I'm Kriba. I'm from BSMS Physics 3rd year, and I'm here to explain my project using Neural Ordinary Differential Equations to predict the ground state energy of 1D spin chains. So, the goal of the project, as mentioned, we want to predict the ground state energy of Heisenberg spin chains using Neural Ordinary Differential Equations, and also we want to compare it with the results produced by feed-forward neural networks. So we have chosen Heisenberg spin chains, but this model can also be extended to other 1D spin chains. Okay, first of all, what is a spin chain? So spin chain is just you can tell a line of electrons or an array of electrons arranged with up and down spins, or like random up and down spins. So each we assume that each spin interacts with its neighbor. It doesn't interact with its next neighbor. It just interacts with its neighbors. And this is also used to model magnetism and quantum correlations. So here we talk about antiferromagnetic coupling, in which J is greater than 0. And this is the Heisenberg Hamiltonian. That is the Hamiltonian for our spin chain. So here we have J greater than 0, and delta is the anisotropy parameter. So what is this? What are these SIX, SIY, and SIZ? So these are called spin operators. These are nothing but h cross by 2 into polymatrix. So these are the poly X matrix, poly Y matrix, and poly Z matrix. So in antiferromagnetic coupling, we say that if two spins are aligned in same direction, the energy is high, and if they are aligned in opposite direction, so the energy is low. So it's easy to see here that if you have just two spins, the energy corresponding to this state is your ground state energy. But that is when these are the eigenstates of your Hamiltonian. In that case, this will correspond to the ground state energy. How to find the ground state energy? So for a spin chain with L sides, each spin can be up or down. So like if we have two spins, okay. So if we have to form a Hamiltonian matrix, we need a basis states. So what can be our basis states? In case of two spins, our basis states will be up, down, up, down, and down. So we'll have a total of 4 basis states. In case of 3 spins, we'll have 8 basis states. So in case of in case of L sides, in spin chain with L sides, we'll have 2 power L basis states. So in this basis states, the Hamiltonian can be written as a 2L cross 2L matrix, where each matrix element is given by this notation. So finding the ground state energy is just like solving the Schrodinger equation and finding for which this En is minimum. So the problem here is these are the basis states, but these are not the eigenstates of this Hamiltonian. So since these are not the eigenstates of this Hamiltonian will not be diagonal in these basis states. So what we have to do is we have to diagonalize this Hamiltonian to find the eigenvalues, and among these eigenvalues, the eigenvalue which has the least value is our ground state energy. So the diagonalized form looks something like this. So here the elements of D, the diagonal elements of D are our eigenvalues, and the least one of them is our ground state energy. So if this is just a problem of diagonalizing, why do we wish to solve this using machine learning? So as you see, if the chain length is 4, we have 16 basis states. So this is the Hamiltonian will be 16 cross 16. For a chain length of 6, Hamiltonian is 64 cross 64. As you can see, by the time it comes, the chain length becomes 10, we have a matrix of 1000 cross 1000 approximately. And by the time the length goes to 30, we have a matrix of 1 billion cross 1 billion. So if we analyze the time complexity of diagonalization, It scales roughly as a big O of n cube. So and the memory also scales as big O of n square. As you can see, the memory and the time blows up very quickly. Memory and time complexity blows up very quickly. This is called curse of dimensionality, and because of this, we can't numerically solve uh, spin chains of larger lengths. So the idea here is, instead of diagonalizing large matrices, we can train a model to learn the mapping. So we just have we input the model as Hamiltonian. We input the Hamiltonian parameters and we get the energy output. So once trained, ML can predict energy quickly without any diagonalization. Now, since we have understood that machine learning is required for a problem, let us try to know which ML architecture is best for our problems. Neural networks are the most common models used in machine learning, especially for regression and prediction problem like ours. So naturally, this is the first approach. But we observe that neural networks perform very well for small systems. That is the one it was trained on. But when we predict it for large systems, the results are physically inconsistent. They produce very large mean square error values. So why does this happen? This happens because the neural network treats the mapping as a static function. But in physics, the evolution of spin chain, or like the evolution of spin chain as the L or J value changes, is not a static function. It's continuous. It doesn't understand how the Hamiltonian evolves with time, or how the energy of a system evolves with time. So it can't capture the underlying differential equation. That is why this does not perform well for the large systems. So now, we want a model that performs well for larger chains. So we use neural ordinary differential equations. So what is a neural ordinary differential equations? So we can say that uh, it is a model that learns a function which is given by f of h comma t, and this function describes how the hidden state h changes over a continuous variable, which can be time or anything. So instead of stacking discrete transformations like in a forward neural network, a neural ordinary differential equations uses a ODE solver to integrate over that continuous transformation. So here we start with an initial hidden state h of 0, and the model learns the function f that governs how h evolves with respect to that variable. Mathematically, we can write dh by dt is equal to f of h comma t. Then the ODE solver then integrates from t is equal to 0 to t is equal to capital T. And the final state h of capital T becomes our output representation, which we can map to the predicted energy. Now the advantages are, it can capture smooth continuous behavior just like our real physical systems. Here the energy of the spin chains evolves smoothly as we change the parameters like j or delta or e, and they're also more stable and tend to generalize better, especially when the data changes smoothly. Now, why do we use nodes in this problem? As I've said, in our system, we vary parameters like the delta or the chain length, and the total energy changes smoothly and continuously. And neural ordinary differential equations are known to best model these type of problems. Contrast to feed forward neural networks, it would try to directly learn a static mapping from from the inputs to the energy. It does not care about the continuity. It treats every case independently. That's why when we predict for chain lengths it hasn't seen before, it fails. But our Heisenberg model or the Heisenberg chain is dynamic. So here, neural ordinary differential equations are a better fit. So this is the graph of predicted energy and the true energy. So if the true energy and predicted energy are almost equal, it means our model has performed better. So this is the y is equal to x line. So if the points lie on this line, it means our model has performed better because the predicted energy and true energy are equal. So you can see this is of feed forward neural networks, and this is of neural ordinary differential equations. I'll come to this graph when I discuss about the when I go through the codes of this. So let's now see the implementation of a model. So first for that we import NumPy and pandas, and then we define a polymatrices. So the polymatrices are nothing but our spin operators. So after defining this polymatrices with the help of the NumPy array, we move on to define the Kronecker product. So what is a Kronecker product? So it is basically it's a product. It helps us to convert from single spin operators to multiple spin operators. For example, if there is an spin x operator that is acting on site phi, and if you have a whole spin chain, to for that spin x operator to act on site phi, you like if the L is 10 and you want it to act on the site phi, you can assume that there are 9 in all the other 9 sites an identical identity operator is acting, and on the 5th site this polymatrix is operating. So the all the other 9 sites will be identity matrix, and this site will be the poly X matrix. Similarly, if we want to act this poly X matrix on 5th and 6th, we have to do the similar way. The 5th and 6th will have this poly X matrix, and the all other 8 sites will have the identity matrix. So we define the Kronecker product here, and then we move on to build our Heisenberg Hamiltonian. So we just, with the help of the polymatrices and Kronecker product defined, we just move on to formulate the Heisenberg Hamiltonian here. So here we are doing nothing but we are just taking the Kronecker delta product and adding the anisotropy energy. So we are just formulating this matrix here. So after building this Heisenberg Hamiltonian, we move on to generate the data needed for a project. So first, let us understand these parameters. So the L values are the list of length chain lengths, and the J values is the J that is defined over here, and similarly the delta is this one. And now this triple loop ensures that all the possibilities of L, J, and delta are considered while while making our data set. And now we find the with this function we find the eigenvalues of our Hamiltonian, and then we find the ground state eigenvalue. We find the minimum eigenvalue, which is nothing but the ground state energy. And having all this data, we combine to make a CSV file. So let me run this. So here what I'm doing is I'm actually making 3 sets of data. So the first one is the training data, and I'm making 2 sets of test data. This is because the first one, as you can see, are trained on the lens 2, 3, 4, 5, 6, and 7. I mean, the training data is trained on training data is made for the values of L 2, 3, 4, 5, 6, and 7. And the first test data is made for L values 8, 9, and 10. And our second test data is made on 4, 5, 6, and 7. So the L values of second test data are the values on which our training data has been trained on, but the L values of the first test data are the values of which are not present in our training data. So we will get a file in this way. Here S1, S2, S3 are the spins, and Lj, delta, and E here is the energy. So here to make we so now since we have generated our data, let us move on to the next step, that is implementing a model using feed-forward neural networks. So here, first we define a class called the Heisenberg dataset. This class reads our CSV using pandas and identifies which columns belongs to spin and which columns belongs to energy. And it also separates the value of separates the L, J, and delta columns from our CSV file and gives the spin columns separately. Now, for each row that represents one spin chain, we collect the spin values in order, and if the chain length is shorter than the maximum length, that is max L, which we have defined as 14, we pair the rest with zeros. This ensures that every sample has the same length, which is essential for feeding into a neural network. Then after this, we append the parameters j and delta to the end of this vector. Now each data point, so in code it is here. So we pad the spins which are of which the length is less than max L. And so each data points becomes a single list like S1, S2, S3, S4 till S14 and J and delta. So it is a single list with 16 elements. And after this, we fit a scale into our data. So this rescales every column so that its mean is 0 and the variance is 1. So this actually makes the training much faster and prevents certain features like J or delta that has that takes larger values than the other features. Like the spin takes -1 and 0, but J and delta can take values like 2 or 3. So this scaling prevents the features like J or delta from dominating just because they have large numeric values. Now next we will move on to the feed-forward neural network that we will be training. So this is just a sequence of fully connected network, meaning that each neuron in one layer is connected to every neuron in the other layer. So we start with the input layer, which takes the vector S1, S2, S3, S14 and J and delta. So it takes this vector and it passes through two hidden layers with 256 neurons each. And then after each hidden layer, we apply an activation function. We use an activation function. This activation function actually just adds a non-linearity to like this activation function just introduces a non-linearity so that the model can learn complex and non-linear relations between the spin and the energy. We also have a dropout of 0.1. This dropout is just the fraction of neurons that are dropped off during training. This is just to prevent overfitting. Finally, this last layer produces a single output. This single output is nothing but our energy value. So mathematically it can be told that a vector, this is just a function that takes input as a vector of 16 elements as we have seen, and it gives a numerical output that is our energy. Now we move on to the next step, that is training the model. First, we define three parameters, which are the optimizer, the scheduler and the loss function. First, let us talk about the optimizer. So here we are actually using an ADAM optimizer. So ADAM stands for adaptive moment estimation. So it is just basically a improvised version of gradient descent. So instead of using one fixed learning rate, it adapts learning rate for each parameter based on how its gradient behaves. So this makes convergence much faster and stable, like especially in high dimensional problems. Next, we define the MSE loss or the mean square error. So this measures how far the predicted energy is from the true energy. So during the training, the model keeps adjusting its weight to minimize this loss value. And then we add a learning rate scheduler over here. So what this does is it watches the validation loss, and if the validation loss stops improving after a few epochs, it automatically reduces the learning rate by half. This helps the model fine tune its parameters and avoid overshooting the optimal point. Now, inside the training loop, we go through all the batches in the training loader. For each batch, we compute predictions, calculate the loss, and do loss dot backward to get the gradients. The optimizer then updates the weights using the gradients. So after each epoch, we also compute the validation loss to see how well our model generalizes. So if the validation loss improves, we say that that model state as the current best. Otherwise, we count how many epochs passed without improvement. So that brings us to early stopping. We set a variable called patience. So we set it here as 30. Okay, sorry. We set it here as 15. So meaning if the validation loss hasn't improved for 15 epochs, we stop the training early. This prevents overfitting. Now, after the model is trained, we move on to evaluation. This evaluate function turns off the gradient calculations and runs the model on the test data. It predicts all the energy values and compares them to the true energy, computing the mean square error. Then to visualize how good the predictions are, we make a scattered plot in prediction energies in the y-axis and true energies in the x-axis. So let me just run the model and explain it. Just a minute. Okay. So here, as you can see, this axis is a true energy, is the actual energy, and this is what is predicted by our neural network. So this is just for the visual representation. You can see the MSE values of after each epoch, and this is the final MSE value. So this plot is just for representation. It tells how the true energy and predicted energy are close. Like if they both are same, they have to lie along this y is equal to x line. So if the more away they are from the y is equal to x line, it means that the less accurate our model is. So as you can see, in this case, our test data is test 1. So as I said in the beginning, I had created two test datas. So this test 1 is nothing but L values are 4, 5, 6, 7. That is the same L values which are in our training data. Just we have changed the J and delta values. So for this, our neural network, our feed-forward neural network is actually very good. But Let us do the same thing. This code is this exact same of the previous thing, just instead of test 1 I have replaced it test. So this is of L8 9 10. As you can see here, this is of L being 8 9 10. So these are the L values that are not present in the training data. So now if we see this, as you can see, now our neural network is not predicting it well. This is far off, because if the predicted energy and true energy should be equal, they should lie along this y is equal to x line, but they are very much far from the y is equal to x line. So in this case, our feed forward neural network does not give much accurate results. So to improve this, we will be using nodes. Now let us implement a model using neural ordinary differential equations. So first we have just imported the libraries needed in this block, and then here this function loads the CSV and prepares the inputs, and pd.read CSV reads the whole file into a data frame, and these two are Python lists that will collect feature vectors and labels. Now here, for each row, we convert a NumPy array, then split it. The code assumes that at least three entries are j, delta, and e. Everything before that is treated as the spin list. But this assumes a column. This requires our columns, CSV columns, to be ordered as S1, S2, S3 till S14 and J, delta, E. If this is in this order, only then we can do this. That is actually a drawback. Now, we know that chains have variable lengths. So neural nets require fixed size vectors. So we pair the short we pair the short chains with zeros up to max L, and then we append j and delta to the end of this vector. Also note that padding with 0, when we pad with 0, it implies that the model must learn that trailing zeros means no spin. Then now, here we set the max L to be 15. Load, train and test sets and print the shapes. We do this to confirm the data pipeline produces the correct tensor shapes. Next, we have a class ODE function. This class defines the learned ODE right hand side of x dot is equal to f of x comma t. Here we implement f as a small neural network in which input dimensions passes through a hidden layer of 128 neuron, which passes through another hidden layer of 128 neuron, and then output, and which is again back to the input dimensions. The final output has the same dimensionality as the input, so that it represents the derivative of x. So conceptually, the model learns how the feature vector should flow continuously through a time dimension, so that after evolving from 0 to 1, we end up in a representation that's easy to map to energy. Next, we see the class node model. It holds the ODE function and a readout linear layer. In forward, we create a time vector t0, 1 and call ODE int, that which integrates ODE from t is equal to 0 to t is equal to 1. We use RK4, a fixed fourth order integrator that's deterministic and avoids tiny adaptive steps that can cause numerical issues in training. Conceptually here, The node integrates the initial feature vector along a continuous depth, and the readout converts the final point to energy. Next, here we set seeds for PyTorch, NumPy, and Python's random. This helps reproducibility. We create a model with proper input dimensions and choose Adam Optimizer with a learning rate of 0.01 and MSE loss because this is a regression problem. Here, training uses mini batches of size 16. In each epoch, we randomize indices with torch.randperm to shuffle the data. And in each epoch, we also slice mini batches and run forward model batch X forward model which integrates the ODE solver and returns the predictions. We accumulate the total loss for the epoch and print progress every 50 epochs. For evaluation, we disable gradients with torch.nograd and predict on the test set to compute the test MSE. Now, after reloading, we read the test CSV, drop the energy column, and convert it to a tensor for prediction. Here, there is also a separate padding step to match maximum input dimensions. Finally, here we compare predicted and true energy values with a scatter plot as we did for feed forward neural networks. So let us see what we get the answer here. So here we have taken an Eisenberg test. So that is for L is equal to 8, 9 and 10. Okay, we have to first install this. Okay, now limitations of nodes. Okay, the nodes assume smooth and continuous dynamics. So if the data has abrupt changes, they may fail to model them properly. And neural ordinary differential equations require specialized numerical solvers and careful parameter tuning. Libraries like torch differential equations handle the integration, but we have to choose methods like RK4 and control step sizes carefully, as we have seen in the codes. And debugging is harder compared to simple feed-forward neural networks. And we can also apply nodes to disordered spin chains. They can model disordered spin chains also very well. And these are the references for the slides. Thank you.